looking at angles of any magnitude, but before we delve into that, we're going to remind ourselves of what exact trig values are, as well as understanding the unit circle. So the first thing is that we have our two triangles here that are on our NESA reference sheet, and we use these to find exact trig values. So we have our first triangle with two 45-degree angles. So it's telling me that I can express sine 45 degrees as being equal to opposite over hypotenuse, which is 1 over root 2. I can do the same for cos 45, which will be equal to opposite over hypotenuse, and tan 45, which will be equal to opposite over adjacent, which is 1. I can also do something similar for my other triangle with 60 and 30. So for example, sine 30 is equal to opposite over hypotenuse. And here I have sine 60 would be equal to opposite, which is going to be root 3 over 2. What we'll notice is that when we go to do cos, that cos is the complement of sine. So here, when I do cos 30, it's opposite over hypotenuse, which is 1 over 2. Sorry, the adjacent over the hypotenuse, which is root 3 over 2. And then I've got cos 60, which will be adjacent over hypotenuse. So notice that they're the complement of the sine. And then I've got here tan 30, which is opposite over adjacent. And then I've got tan 60, which is opposite over adjacent, which is going to be root 3. So finally, I'm going to move down to understanding the unit circle. So the unit circle, we have here our 3 trig graphs of sine, cos, and tan. And then in this section over here, I have something which refers to the unit circle. And what it does is it's split up into 4 quadrants. So this here is going to be my first quadrant, my second, my third, and then I've got my fourth right here. And here, this A stands for all being positive. Here, it stands for only sine being positive for this one here, only tan being positive, and only cos being positive. And we normally refer to this as all stations to central, as a way for us to remember the order of these quadrants. Now, what it means is that if I take, for example, these quadrants are 90 degrees. So I have 90 degrees here. Another 90 would make this 180, 270, and 360. So what it's saying, and also this 360, I actually start here on the very right-hand side. And what I'm doing is I'm starting from here and I'm working anti-clockwise all the way back around, which is why I start at 0 and end at 360 in the same spot. Now, if I start at 0, notice that if I go from 0 to 90, and if I look at my sine graph, my cos graph, and my tan graph, can you see that all of the output values are positive? Whereas if I move to the next 90 degrees, so let's just say I move from 90 to 180, can you see that sine is positive, cos is negative, and tan is negative? So here in this second quadrant, sine is only positive. If I continue looking at the next 90 degrees, from 180 to 270, sine becomes negative, cos is negative, but tan is positive. So what it means for this quadrant is that only tan is positive. And lastly, what we can see in our fourth quadrant is that from 270 to 360, here sine is negative, cos is positive, and here tan is negative. So therefore, what I can say is that only cos is positive in this quadrant. And that really helps us when we're finding the value of an angle, particularly if we're looking at a range of degrees from 0 to 360, because there's more than one possible solution. And that's what we're going to look at in these examples here. So angles of any magnitude. So notice already that I'm looking for the values of theta between 0 and 360 degrees. So if I look at cos 1 over root 2, I know from my perfect triangles that theta will be equal to 45 degrees. But now I have to consider the range of possible values, and I can do that by looking at the unit circle. So I'm going to draw up the unit circle here. So all stations to central. Now what I need to look at is notice that my answer here is positive. So that means that I need to look where cos will be positive. So cos is positive in this first quadrant A and this fourth quadrant C. Now when I'm measuring these angles, what it's saying is that I always measure from the horizontal axis, and notice from here to here, the angle is going to be 45 degrees. Also notice that my other angle is also going to be in the fourth quadrant. And notice that it too needs to measure 45 degrees from the horizontal axis to this line here. Now, because my unit circle works anti-clockwise, I'm starting here at 0 and then I'm working my way all the way around. So what that means is that when I go to calculate theta, I know that the first 45 degrees is positive because I'm starting at 0, but because I end up at 360, can you see that when I start to work anti-clockwise, I have to stop here, which is 360 take away 45 degrees. So then what I have for the values of theta is 45 degrees and 315 degrees. And that 315 is this red value just here. So if I want to double check, I can actually put cos 315 degrees into the calculator, and then when I do, I will get an answer that's positive 1/√2. So now let's look at example B. Now B is different in that I've got a negative value here. I've got minus the square root of 3. So to find the value of theta, I'm going to use my perfect triangles. And what I know is that from my perfect triangles, is that tan theta is opposite over adjacent. So here I know that my value of theta is going to be worth 60 degrees. However, I've got a negative answer. So when I go to draw out my unit circle to find all my possible values of theta, all stations to central, I need to look where tan is negative. And tan is negative in the sine and the cos quadrant. So what that means is that when I go to draw my angle, the angle that I am making with the horizontal axis is going to be 60 degrees. So that means when I go to measure starting at 0, when I go to measure all the way here, can we see that theta will be equal to 180 degrees less 60 degrees? So it will be equal to 120 degrees. Can we also see that the other angle lies in this quadrant here, and it should make 60 degrees with the horizontal axis. So it's going to be this angle right here. So when I go starting from 0 and I work anti-clockwise all the way over here, can we see that my final degree will be worth 360 minus 60 degrees, which will be 300 degrees. So therefore theta will equal 120 degrees and 300 degrees. If the question is why do I have to do both these quadrants, is because the unit circle, one full rotation, so if I went all the way around here, all the way back, is 360 degrees, an angle of revolution. And if I go back to the start of my question, we can see that the domain wants the range of values between 0 and 360 degrees. Lastly, we have one here and it's not a perfect triangle, but that's okay. So here we'll actually use this one. We'll make it to the nearest degree. And if we don't have a perfect triangle or a perfect value, we can still work this out by simply doing the inverse sine of 4/5. So theta will equal inverse sine of 4/5. So when we put that into our calculators, we end up with approximately 53 degrees. Now we work this out the same way we did before. So I draw out my all stations to central. Now notice that my answer is positive and sine is positive in the first and the second quadrants. And I'm making angles with the horizontal axis. I'm making this angle here of 53 degrees and I'm making this angle here of 53 degrees. So I'm measuring 53 degrees and I'm measuring 180 less 53 degrees. So my two possible solutions are 53 degrees and 127 degrees.